as much as I would like to charge off into a whole variety of numerical examples encountered in a variety of different engineering situations, we've got a quote theory kind of thing that we have to do first, and that is this expected value, which in many ways is a very simple, direct kind of thing, yet historically tends to confuse folks quite a bit. And that's because it has a lot of subtle nuances to it that turn out to be crucial in terms of application later on. And this notion of expected value is that first and foremost, it is a mathematical operator. And part of what happens in probability is that we have phrases that are used to sort of characterize things, and it can fool us. And expected value is one of these. Expected value is often used as a phrase for the mean, and that's certainly one example of an expected value. Remember, the mean was equal to mu, that Greek symbol mu, and when we write it in terms of the expected value, let's say our random variable is x, it'd be e square bracket and x, where e is a functional operator. And its definition here is that we're going to take all of the possible values of x and weight it by the likelihood or the probability that x takes on that value, and sum that over all of the values of x. We saw this before in the context of the inner arrival gaps t, so I just replaced the symbol here, right? And I'm going to put off in words here to the side that these are weighted values of x sub I, weighted by the probability here. Right, now I'm going to also put quotes around that because we're going to generalize this in the following kind of way. Because remember that our variance, right, was equal to a very special kind of thing. And leave yourself a big gap here that its definition here for variance was that we were going to take the deviation away from the mean, we were going to square that, so square deviations away from the mean, and then weight it by the chance that a random variable was located there, and sum all those up over all x. All right? Well, in that case then, the expected value, the stuff that goes in the square bracket, is x minus mu quantity squared. So notice the pattern here, and that is that the expected value operator is going to take the stuff that's inside, the argument that's inside, right? So there that is, and we're going to weight it by the possibility that it happens. So yeah, it's true that the expected value is an average, but oftentimes, and here's one of the subtleties, people stop at this first level. Oh, it's the average. Okay, bam, I'm done. Well, now it's the average of a function that's sitting in here, right? So it's a little bit more than just a simple average. It's an operator. It's an operator just like sine and cosine, although sine and cosine are what we call nonlinear operators, right? And the expected value actually turns out to be a linear operator, and that is of great help to us. Right? So note that here's our expected value of the squared deviations, right? Written out over here, and it's all its glory. And that we can take this term and we can expand that product. When we do that, it's important to keep track of where the summation is, and it's over all of this. Right? And so we'll have xi squared minus, and then 2 times mu times xi, and plus the square of mu, and all that gets weighted by probability mass function. Right? So that's the first step here, and then note that we can now, because summation is linear, right, we can break this instead of a sum of one big long expression, we can then break this into a series of 3 different sums. And so this first one would be the sum of xi squared times probability mass, right, minus, now mu is a constant, so, and so is 2, so that can be pulled out of that expression. And then likewise at the end here, we can pull the mu square out. And so implicitly here, there's brackets to indicate that we have 3 different sums. Now we can do a couple of things here to simplify some things out. The first off, which is, notice that this first one is the weightage, the weights of the values of xi squared. So in other words, that's the expected value of just x squared. Right? Notice in the second case that this little piece here is the very definition of mu. Right? And that in this last case, this right here, we're just summing up all the probabilities. Remember, this sum is over all the xi values, right? So by definition, when we sum up all the probability masses of all associated with all the different values of x, we're going to get exactly 1.0. Right? And so that means that, oh, this is minus 2 mu squared plus mu squared, and that simplifies then down to minus mu squared. And that is going to be a very useful identity down the road. And it also illustrates here how the expected value, since in this discrete random variable sense, right, is equal to a sum, a series, and that's a linear operator. So expected value itself is not only just a mathematical operator, it is a linear operator. Okay? That's important. Now, other aspects and properties that are useful to take note of here is that mu is our centroid. There's a mass analogy that's going on here. And sigma, our standard deviation, right, is coming from the square root that's associated with the second moment of area. Right? If we think about our second moment associated with the mass, right, and if you go back to your statics class where we talked about the second moment of area, or moment of inertia, we sometimes call it, right, that we end up with, because the area turns out to be 1, the mass, total mass is 1, that sigma is, from a geometric analogy, equal to the radius of gyration, square root of I over A, where A is equal to 1.0, and I, our second moment of area, is coming from this expression up here. So what's really kind of nice about this is that if you feel like you have an understanding of centroids, how to find a centroid, if I gave you a basic geometric shape, you could get the centroid. If you feel like you can understand how to get the radius of gyration, you've already got the mean and the standard deviation licked. Right? It's just a slightly different kind of twist in thinking about things. There's also a terrific analogy to rigid body dynamics and the mass centroid, right, center mass, and the angular moment of inertia as well. Right? So you start thinking about figure skaters spinning, and as they bring their arms in, they are reducing their spread. Right? They're bringing their mass closer to the center, so the angular moment of inertia gets smaller and smaller, and that's also what's going on here too. This radius of gyration kind of concept is very useful to us as an analogy.